Okay, let's start this session. Okay. So, good morning. Let's start this session. Let's try to little bit review what we have learned before. So, let's say this is the given circuit. We want to see what is the operation point of the transistor. The operation point means we want to know what is the collector current, right? And what is the VCE, basically, to check if the transistor is inactive or which region, right? So let's try to solve this circuit and find the IC. So we can assume the beta of the transistor is 100, the VBE on is 0.7 volt. Let's try to find the collector current. The supply voltage is 4.7. What do you talk about? Okay. You have fun yesterday. حتى وبعد كده امتى Still use the pen. Can not give you for finding my name. Yes. I see. Yeah, we have this thing. Try this one. Okay. And then what's coming? This through. So for the simplicity, you can assume the phase current is small. It's really small. So it's a little bit provide your calculation. If you assume the phase current is almost negligible, then your life would be a little bit easier.
Doctor, I
Yes.
think I finished.
How much is the IC?
1 milliampere
Right.
and the VB is 1.7
VCE, right?
or VC. So
Yeah, VCE. Right, IC is 1 milliamp. VCE 1.7.
7.
Okay. Yeah. So can you tell me what is the small signal parameter of this device, especially the GM? You remember? First, if is the transistor in active or saturation? Active region or saturation region? Is active, right? Right. Active means what? Active means VB is on, this junction is on, the other one is reverse, right? Right. Why the other one is reverse? Because if you calculate, here is 2 volt, the DC, here is 2.7 volt, and here is 3.7 volt. So the top one is, the top diode is reverse. So we are in active region, right? Saturation means what? In BJT, saturation means that 2 diodes are turning on, right? So this is in active region, so assumption of the beta of 100 is correct. The device can have the gain. Then you can put the small signal model, and for the small signal model, what we need is what? The GM, right? So how much is the GM for this device under this condition? Under this condition, right? Yes, GM is IC over VT, right? IC is 1 milliamp. VT roughly at room temperature is 25 millivolt, basically, which will be 1 over 25, right? Is the GM. So then if we make some amplifier using this, let's put some DC block capacitors, right? We don't want to corrupt the bias. We apply a V in, and we have some load resistor, but let's say the load resistor is 100 kilo ohm, and here is the V out. So what is the voltage gain from V in to V out? How to find it? Let's try to find the voltage gain. So you can, so I just a little bit simplify it as the AC small signal model, right? It doesn't help that much, but I just do it until you tell me the answer. 20 kilo in parallel, 27 kilo. Kilo. 1 kilo. Let's say parallel to 100 kilo. Where is the V out? I simplified it a little bit. Right, this is the IC. So what is the voltage gain? How you calculate it? Let's see. We don't need to memorize the formula, but it's possible to solve it yet. If you tell me, I can write it. We also don't like to draw the small signal, expand it that much. So if you want, you can just put some small value for R pi here, right? Some RO here. But there is some GM something here, some current source, right? If you want to just remember that. So we don't need to consider this R out at the moment. It makes it a little bit more simplified.
Parallel with the 27K, parallel with the R pi, and all of them will be series with the 2K. This will be the V in. V out is the.
No, V in already is at the base basically. So I mean this 20 in parallel with 27K is not doing that much because you already applied the voltage here, right? So these two resistors are just something in parallel at the beginning, but doesn't have anything for this circuit. It changed the input impedance, right? It changed the input impedance that this V in source is seeing. Everything seen from the device, it will be in parallel with 20K and this term, right? So we can actually write that. So first let's then find the input impedance. What is the total input impedance? Let's start from that point. Yes. R in is 20K parallel 27 parallel R pi. Is that it? But from the input side, I mean from the transistor side. This R pi is not just something to the ground, right? You see, the R pi, if here was grounded, you were correct because there was R pi to the ground, right? Can you see it?
Series with
It's not just series. So if you remember, so yeah, if you remember, this 2K is at the emitter, right? You can move it back to the base side. This resistor, right? So once you are moving this resistor to the base, what will happen is the value will increase, right? Because the base current is low, so the impedance is high, if you remember, right? So in fact, the R pi is plus 2K times beta, right? 100 plus 1. 1 plus beta, right? So this is the input resistance, right? Right. So then how about the gain? How about the gain? Can you tell me?
100K over Rn.
So I just roughly tell that these two are just 1K, right? Because 100K is much larger. Okay. The gain would be what? 1K. There's a negative sign, remember? Right? What else? Hotel. Rn is what?
7 with the R pi plus 2K
Let me
V
write it.
plus 1.
Oh, okay. You are saying Rn here, right? What plus what? You mean just this? Is this the gain? So can you repeat so that I write it? You mean like this? Oh, so we already have it here in Rin, right? Rin is here, right? So basically V in is already here, right? V in is here, already at the base, right? We need to find this collector current from this V in, right? Right? So you can actually move everything basically to the emitter side first. If you move everything to the emitter side, then this R pi will be 1 over GM, right? It will be like this. And then this 2 kilo ohm is there, right? And you are moving this V in basically to the emitter. Then this will be the emitter current. This emitter current is what? V in divided by these two resistors, right? So the emitter current is basically this V in divided by 1 over GM, right? Plus 2K, right? And once you have the emitter current also is almost same as the collector current, right? And then this collector current is passing through this RL, which is 1 kilo ohm, right? So V out basically is IC times basically negative IC times RL, right? So you already find the IC, put it here. So what will remain is basically this 1K is the RL, and then you have 1 over GM plus 2K. So this is the voltage gain, right? Then how much is the value? Is this clear? If you need, we can. So how we are solving? First of all, we know that the V in basically is at the base, right? Because it's just connected, right? V in just comes to the base, right? Fine, so far. I just connect this voltage source just to the base, right? And then I want to find the collector current due to this V in, right? So you can draw simplified or transferred impedance to the emitter first. You moved everything to the emitter because you want to find the emitter current. And emitter current is almost close to collector current, right? So if you want to go to the emitter, so you just have this R pi, you transfer it to the emitter, right? R pi divided by 1 plus beta, which will be 1 over GM, right? This 1 over GM basically is transfer of the R pi to the emitter. And you already have this 2 kilo ohm there, right? They will be in series. And then you have this V in across these two resistors, basically, right? And then this gives you the emitter current. So once you find this emitter current, then the IC and IE are similar, right? Almost. And then you can tell that this is IC. IC is passing through this output resistor. If you multiply this IC to this value, to the resistor, actually showing the voltage across this resistor, right? So since one side is ground, so it's basically the V out, the other side, right? Is that fine? This is the way you can think. So can you tell me what is the value of the gain now with this circuit? It's almost half, right? Because it's how much? 0. Yes, right? Because the 1 over GM, you remember, is considered a small impedance. So it should be close to 0.5 is correct. So how can we increase this gain? The gain is not gain actually, is less than 1. How we can increase? So what is the reason that this gain is low, basically? Which impedance? Yes, if the 2 kilo ohm was 0, basically, in this equation, actually, you could see, right? If it was 0, then the gain would be higher, right? So how we can get rid of this 2 kilo ohm in the AC, but still we want to keep it as the DC, right? we add some capacitor, right, to short circuit the 2 kilo, right, for the AC signal. And then if you do so, what would the gain? What will be the gain? What will be the gain if we bypass, basically? We call it the bypass capacitor, right? The gain will be how much? The gain will be how much? Right? It's 40. GM times 1K, right? Right? If you make this 0, then the gain will be 40, negative 40. Is that clear? So it means if I apply some signal with 1 millivolt amplitude, at the output you will get something around 40 millivolt, right? So let's see how it works. So basically here is the same circuit. So I just firstly remove this cap. I just put a value of 0. 0. I speed no. Um let's but oops. Okay. Set the cap. Yes, I need to bring the mouse. Let's So I put this as a 1 millivolt AC source. And then let's just remove it for now. Reduce this speed a little bit. Three point 2.7. First, let's make y. So let's first make this again 0. Okay. So first of all, let's see if that biasing points that we calculated is correct or not. What is it showing is it looks something wrong, isn't it?
maybe refresh the page.
Uh, or maybe this value is too large. So needed to be larger a little bit, 2.7. Now it's fine, I guess, right? Is it? I'm just checking the DC of the transistor over this right corner, bottom right corner, right? The collector current is almost 1 milliamp, right? This is the same circuit we solved. PV is 0.6, right? VCE is 1.5. We calculate 1.7. A little bit current is higher, so because we assume that VE is 0.7, now is almost 0.6. Right? This is fine so far, right? And then let's start adding some AC signal, let's say 1 millivolt input signal. Let's see how it works. So the one problem is that okay, I need maybe let the simulation go faster. No, still too slow.
But maybe it's the extra wires.
No, actually, I know what is happening actually. I put a large cap, but the cap it takes some times to reach to the final DC value. The cap is so big. Is impractical, in fact. So I reduce the cap value, see how it will be. Still bit. Uh, So you are saying that this side of the curve is going up. Actually, the DC of the output voltage is settling. The DC, so I am going fast until it's settled down first. What is happening is this 500 microfarad cap at the output is getting charged to some value at the DC, and the settling time basically is the time constant between this 100K, 1K, and 500 microfarad. So now it's almost reaching. Still is not very well settled.
This way as well, practically. We have to like turn it on and wait a little bit.
Yes, of course. Yes, but this simulation speed is less than the practical speed of passing time, almost, right? And we usually actually this is also important. So once you design this, you need to design this value of the capacitors and things so that once it is turning on, the settling time is reasonable for your application. If too long, then sometimes you cannot afford. So let's see, two. So actually, I want to find the gain, but still long time to reach the final value. What if I make it 10K, make it a little bit faster, maybe? Or so we're waiting this to settle the DC. In fact, I want to find the gain, right? Still can find the gain, basically. So the input basically is 1 millivolt, right? The amplitude, right? The peak of the input is just 1 millivolt, right? The output is not only one. I mean, the output we expect to be less, right? The gain is less than roughly half. So the peak value I'm just seeing is 4 millivolt, right? And then the negative peak is what? It's 3 millivolt. So can you tell from these two how much is the amplitude of the output? Right? Because the output still has some DC. I wanted to just read this number over here, but this number is just because it already has some DC. Is is not good to refer. So we can just measure it like this. The peak is like around 4, right? Less than 4. The minimum is 3. So the peak to peak amplitude is almost 1. It's less than 1 actually, right? And then the amplitude is almost half. Did you get it? I wanted to spend more time so that this settles down and then we can just read over there. But it takes longer time. So now the gain is not that high, right? And then what we were proposing was to add some cap here, right? A big cap. Maybe I just put like the big value again here. And then we expect to reach some gain of like 40 something, right? So let's see. I'm not sure if this cap value is big enough for this frequency. So now the positive cycle is negative 51, and then this one is 100, so is peak to peak is almost 50 millivolt, right? 50 millivolt means 25 the amplitude. So the gain is higher, but it's not as high as we expect. I guess this value is still is not enough, so maybe I go for a larger value. But the larger value, it has the problem of the settling time. So let's see. Actually, we can increase the input frequency and reduce the cap value. But the problem is this does not show very well. So if you increase the frequency too much, then everything is just very, let's see. Ooh, it's 6. Let's wait, see how much is the value now. So here is negative 460, yeah. 600 something. 400 something is, yeah, it's less than 200. Yeah, 150. Divide by 2 is something that right more now, more than what we expect. So actually still the DC may not settle down as we expect. You see that DC, this is not DC, in fact, it's under the situation. But the collector current at the moment is higher since it is not settled down. So the GM is higher. Maybe that's why the gain is higher. So, but here, this is what was a good exercise, since you are also seeing that in top of the AC, these capacitors are making some transient time, right? The transient time of these caps actually takes time, the bias of the circuit to settle to the final value. And after settle to the final value, then you can tell what you have done is how. So let's see if I can increase this frequency initially, like 8K, and then reduce this value to something more reasonable. And micro. Yes. No. It's very difficult. It's a very big cap, right? So something in the range of millifarad is already very huge cap. Yeah.
The differences are in the micro usually.
In the electronic circuits, usually it's in the micro range. 100 micro is almost the max. So now this is already settled, right? But since the frequency is too high, so you cannot see the sinusoidal thing, but at least you can see the amplitudes. So the input amplitude is like 1 millivolt, right? The output amplitude is almost 34 millivolt. So the gain is kind of less than 40. We calculate 40 is a little bit less, right? But it's close, right? So I'm not sure if I reduce the frequency from now. Do you have any idea we can scale the horizontal axis so that we can see the sinusoidal clearly?
Here, sitting
Where is it? Where? Do you know? There should be some setting. Uh, where is the mouse? I can zoom in, zoom out a little bit, but okay. How about this? Okay, better. How about the output? So scale. Okay, now is better, actually. Now is better. We can reduce a little bit the frequency. I guess it doesn't need to be this higher. Maybe 4K. Okay, now is okay, right? Now is better. So one question. So what if you increase the amplitude of the input? Like what if I increase the amplitude of the input 10 times? Yeah, the output should be 10 times more, mean that it should reach something around 340 millivolts, right? Let's start. So it's okay so far, right? It is increased, but the gain is not as high as the initial estimation. The gain is dropped a little bit, right? Why this is happening? No. I mean, initially, once the input was small, the gain was 34, right? Now we increase the input 10 times. So we expected the output also reach to 340 something, but it's less than before. What is changing? We are changing the input, but the gain is less than, once we increase the input, the gain is less than what we calculate initially. Why this is happening?
Because they are not balanced with the DC.
This is correct. Actually, once the input is becoming bigger, right? Our initial assumption was for a small signal, we were saying, right? The small signal means what? You are not changing too much of the DC, right? You are almost at the DC values, but this very small, tiny signal is you are applying to it, right? But if the signal that you apply to the input is very large, so in fact, you are basically changing the whole DC, right? So this assumption for the small signal is not valid anymore that much, right? Right. So the small signal model is what we come up with the GM and everything. We are just assuming very small, so we just take a derivation, right? The derivation is we are just assuming the GM is for very tiny variation around the DC. But if the variation is larger than what you assume, then the operation point of the device basically is changing, right? And then it means that the GM is keep changing over the cycle, for example, right? So what if I increase furthermore? What do you expect? if I increase the input like maybe 5 times more, like 50 millivolt.
Be less than 1.5.
So yes, from from this we already know that, but some other thing you can also see will happening. The waveform is changing, right? Why this waveform is changing? No, the capacitors cannot do some. Actually, the capacitors, you can tell that they are short at this frequency. It is a distortion, right? The distortion means what? Means that your circuit is not linear anymore, right? So the input is something sinusoidal. It has changed it to something else, right? It's because of some nonlinearity of the device. So the linear circuits and systems, right? You expect just multiply the input by something. It doesn't change the frequency content, basically, right? The linear systems. It's just multiplied it or phase shifted, right? It doesn't change the waveform. But now you are seeing the waveform is changing, right? The waveform changed because the frequency content of this output is changed because there is some nonlinearity, right? So basically, what if I furthermore increase the input? Let's go a bit more even. What is happening? Right? It is going to some region that will be like more like a square. So why this square waveform is, I mean, why the output will be like the square? It looks like that there are two limits from the top. Let's stop it. From the top, there is some limit, right? It looks that it cannot go higher than this value. And from the bottom, it goes to some limit. How can we know where are that limits actually? It depends on the DC. Yes. So how? So why is the maximum is 4.7? Is it 4.7? Let's see. The top is 800 something millivolt. The bottom is negative 1.7. So it's how much now? 800 minus 1.7 is 2.5 or 2.6 something. So it's not exactly 4.7. So could you predict these levels? Can you tell what is happening? What can you try to describe? It's not half, but there is some relation, right? So in the extreme cases, what will happening to the transistor? Yeah. What is the reason of that clip? It is, it is, right? So the operation region of the device is changing basically, right?
Yeah, we are having voltage breakdown.
We are reaching to not the breakdown, but we are reaching so let's think like this. So you have this circuit, right? You are trying to apply some input voltage here. That's sinusoidal, right? This sinusoidal thing is actually increasing this base voltage at the positive cycle, right? So what will happen? This base voltage increased. The current of the transistor is increasing, basically, right? The current of the transistor increased, then this voltage will be lower, right? Because this current is passing through the 1 kilo. So this voltage is starting going down, right? That's why we have a negative sign. Means that there is 180-degree phase, right? Once the input is going up, the output is going down, right? But this voltage, how long can goes down? So initially the DC point was 3.7 volt, I guess. Maybe um, maybe we can draw it here. You have this 2 kilo ohm. Here, initial voltage was 2 volt. We have the cap. Here we have the 1 kilo ohm, 4.7 volt. The DC was 3.7 volt initially. And here the DC was 2.7 at the base. And then I just show it that we are driving it with some Vin. So this voltage is going up. The current of the device increases. So this voltage is going down, right? So how long this voltage can go down? How far? The maximum. Input can go, let's say anything, but there is some limit for the output, right? The output,
The cutoff.
it reached to the VCE sat, right? Because the VCE is initially what? The VCE is initially, let's say, 1.7 volt, right? Do you remember? Initially, when there is no input signal, the DC values is like VCE is 1.7 volt, right? And when you are applying some AC on top of this, then this voltage is start going down, right? Until this voltage reach to what? I mean, the VC is becoming lower and lower, right? Until it reach to the VCE sat. VCE sat, right? The saturation, which is normally like 0.22 volt. Do you remember? Right? So it means that this voltage from the DC can goes down to like, okay, another thing. So in the AC, actually this cap is big enough, right? This cap at the emitter is big. So once it's big enough means that it keeps this DC value like 2 volt always. So basically the emitter voltage is not changing. Can you understand what is the reason? We have a big cap at the emitter, right? The big cap basically means that it is not changing. It is difficult to change the AC voltage over the big cap. There is not much AC signal on the big cap. Only the DC is there. Can see. Can you see this? So this a bit. So we try to let's do it a bit more clean. We try to find where is the limits of the output variation now. Right? Because that thing also important. So here you bias the emitter voltage like 2 volt. Here was 2.7 volt, the DC, right? And then you are adding some extra voltage as the input, AC signal, right? This is 4.7 volt, right? And here is the output 3.7 volt, right? Initially. So the question is, once this signal is going up, the input signal, how the output voltage varies, right? Right? The base voltage is increasing, the collector current is increasing, and then this voltage is decreasing, right? And then the the ratio of the increment is like the gain, right? With this value of the gain, this start dropping, right? So I just try to plot the time domain, the VCE of the device, basically. So first of all, the emitter voltage does not have any AC variation. Why it doesn't have? Because of this big cap. So the big cap here does not allow that the AC signal can appear at the emitter, right? Because for the small signal, if you remember, once we have this, actually the small signal model for the cap at the emitter is like a short circuit, right? The small signal model at the emitter is short circuit means that there is no AC signal at the emitter. Is that clear? So you can tell that the emitter voltage is always 2 volt, right? But the collector voltage is changing based on the IC and the gain, right? So initially is once there is no input signal is 3.7 volt. But once you are applying some AC signal, it is just varying around this 3.7 volt. Actually, let's this is VC, right? Not 3.7 volt. This is changing around the 3.7 volt, right? And then the VCE is how much? VCE is actually is 3.7 minus 2 volt, right? VCE is initially is 1.7 volt, right? And then it is varying around this 1.7 volt, right? So what will happen once you are increasing the input? This variation also increases, right? Once you increase the input signal, right? But if you increase the input signal even more, so the variation also should be more, right? Should be like this, right? Normally should be like this. But this is the VCE, right? The collector emitter voltage. And then we are seeing here is actually sum of the part. The collector emitter voltages have to be negative. But is it possible the collector emitter voltage to become negative? The VCE, the minimum can reach is like 0.2 volt. If we just make it simple, we can say that can reach to 0, right? Just simplify it. So it means that the VCE cannot be below zero. So it will be cut from zero, right? So what you will have basically is something like this, in fact, right? It cannot go below certain level, right? This is why you are seeing in the simulation that the bottom side is like becoming like limited to some value, right? On the other hand, how much this VCE can be at the max? So we are seeing that the VCE at the bottom line is limited to 0.2, right? Or zero almost. What is the maximum? What is this maximum here? So we should do the same thing reverse, right? So let's say for the maximum, the input is getting lower and lower, right? The output is getting higher and higher, right? From 3.7, how far it can goes high? So just let's think, we are reducing the input, right? Reducing the input means we are reducing the collector current. Is that fine? So what is the maximum reduction of this basically collector current, you can say? The maximum that we can reduce the collector current. Because this reaches zero, right? You had to bias the transistor to some certain value, right? Now you are trying to reduce the base voltage, so you are turning off the device, basically, right? The maximum that you can do is just turn off the device, right? Basically, no collector current. And once there is no current, then what would be the maximum of this voltage? The 3.7 volt or the V out. What is that voltage? If the collector current is zero,
Will be 4.7.
right? So this collector voltage from the top basically can reach to 4.7, right? The VCC, right? So basically, you know that the collector voltage from the top is the max is 4.7, but the minimum is what? The minimum is reaching to basically the emitter voltage, right? So in fact, if we have the V out here, the V out was starting at 3.7 volt, right? And reach to 4.7 at the max. That's why it becomes like again like square shape. If you try to push it more, it cannot go. It just clip, right? And from the bottom can reach to something around 2 volt, right? The emitter voltage can go down to like 2 volt. And if you try to push it more, it cannot go. It will be like square. Yeah. Is that clear?
So if we try this practically,
Yes.
will it not damage the transistor?
Depends. If you press put more pressure on it, it might. But the current and voltage depends on how much the current and voltage is actually burnt inside the device. So sometimes you reach to some current limit for the device. Sometimes you are reaching to some voltage breakdown of the device. So it might, if you haven't designed carefully, then it might reach to some of the damaging point. but not necessarily. It just sometimes it's just clip. It's not always damaging. So now, can you tell how much is this peak-to-peak variation at the max? 2.7 roughly, right? So actually, we expect to, in the simulation, we also reach this value. I don't know if it was. So let's see. So this point is 800 millivolt, right? The bottom is 1.8 is 2.6. It's almost there, right? This voltage is after the capacitor. So that's why you are seeing that there is no DC, basically. If I could measure this node at the collector, we should have seen that shift of the voltage reaching to 4.7 and from the bottom reaching to around 2 volt, right? But this voltage is after the DC block, so the DC already is gone. So that's why it goes positive and negative because there is no DC. So in fact, once you are designing this circuits, you can actually uh, define the operation point, in fact, to basically to reach the maximum swing, basically. This we call it swing, right? The output swing means that the voltages can goes from where to where, right? So now, if you are seeing from here, the DC voltage of the bias is 3.7 volt. It can goes 1 volt up from the DC level, right, to 4.7. How much goes down? 1.7, right? So it means that if you apply a sinusoidal thing, it will start clipping from the top earlier. So let's try to. So you have 3.7 volt, right? Initially, you are having 4.7 volt here. The clipping part, you are increasing your amplitude of the sinusoidal thing. Up to here is clean, right? If you increase furthermore, it start clipping from the top, but it still has room from the bottom because the bottom, the limit is 2 volt, right? So basically, this is not very optimum operation point for the biasing of the device. I mean, this 3.7 is not a good point. It's not the middle range. So if you design it perfectly, you try to make that the DC is always have same distance from the top and the bottom of the clipping point. Now from one side is less, from one side is more. So it would be better we basically reduce this 3.7 volt to the center of this line so that we could have a larger sinusoidal thing with less distortion, right? So is this clear? So in fact, if you want to design a more linear amplifier, so you need to adjust this 3.7 to be how much? Right? 4.7 minus 2, right? Divide by 2. I'm just trying to find the maximum amplitude, right? Plus 2 divided by 2, basically, is 3.35, right? So it is better to increase this RC value. So once you are designing, so that initially this voltage drops a little bit more to this value so that you have more symmetrical swing, right? You you will uh, distort the signal less than what currently is, right? So what if I increase this 1 kilo ohm to 2 kilo ohm? Actually, I'm reducing this voltage even more, right? The DC will comes down to 2.7 volt, right? The gain is increased. The gain is increased, but the DC drops to 2.7. And then the signal will clip earlier from the bottom. Do you see it? So if I increase this RC value to 2 kilo ohm, right? Basically, the clip from the emitter is not changed, is already 2 volt. From the top also is not changed, also 4.7 volt, right? But the DC that I biased is around 2.7 volt. So if you apply the signal, initially is okay, right? If you increase the amplitude, it start clipping from bottom earlier, right? So the distortion is happening earlier. Distortion is happening earlier, right? So the best is always you try to bias the collector emitter so that this distortion happens at the same time from both sides. Is it clear? Right? Okay. So now I guess now you got some sense how the large signal this actually analysis is just large signal. We are seeing how the transistor behaves for the large signals, right? Now we know how the large signal may change the signal, how the small signal gain is calculated, right? And how we can see all of these things together, right? Basically, these things together is required, to design the amplifier. And then I wanted to continue a little bit more on the slides, which today is supposed to go to, where is this? We go to the MOSFET. Let's start the MOSFET a little bit today. The MOSFET is not that new for you, I guess. It should be okay. We move faster actually for the MOSFET because the concepts are pretty much similar, just the device itself is a little bit different, right? Uh, okay. So let's a little bit go back to the device. Uh, okay. So here it's trying to see how the MOSFET's actually operating as a transistor. First of all, MOSFET is what? Metal oxide semiconductor. What does it mean? Basically, you have a semiconductor or substrate here. You have some insulator, which is this oxide. the oxide, silicon oxide is an insulator, and you have another metal on the other side of this insulator, right? Some metal contact on top of the insulator is this region, right? You have insulator, which is the oxide, which is actually silicon oxide, is an insulator. And then you have the semiconductor substrate at the bottom, right? That's why we call these things MOSFET, MOS. And basically what it forms is a capacitor, right? Because you have insulator, you have a metal, you have a another side of the cap, some semiconductor, right? So if you apply a DC voltage, since it's like a cap basically, right? It can store some charge, right? It stores some charge. And then the other side also a negative charge, right? So initially, if you think here, actually initially, if you think here, there is no charge in this p-type, right? So the hole there are some holes because this silicon is like p-type, right? The carriers basically are the holes, right? But once you apply this voltage, basically you are making this charge trapped at the edge of this region, right? The plate of the capacitor. So basically it tries to actually absorb some of the free electrons over here, and the holes will go back a little bit from this side, right? So now you are seeing that you will have some sort of free electrons at the edge of this surface. And then if you apply a DC voltage from this side to this side, then this free charge actually can move from this direction to this direction, for example, right? This is how the MOSFET is supposed to work, basically. So again, this is a 3D uh, demonstration, right? Here you have this semiconductor material. Here you have this insulator thing, insulator, which is oxide, right? And the top, which is, we call it the gate, is something like the conductive plate, is a metal thing. This is the metal. And in 3D view, you can see that there is a cap form from this semiconductor region to this gate, right? And if you just look at it from the side, we usually draw it like this, right? And the way we get access actually, so you remember from the sides, we are trying to get some access, some contact to have the current, make this current happening, right? This side access is a, we bring it up from this region, from this N plus region. We bring it upward instead of the side, right? And if you look at it from the cross section, it will be like this. So initially we were saying that we put the contact from this side, right? And then here was the negative charge, and we try to apply some voltage from here, right? But this, we don't have access from this side, so bring it up from the top, right? So this is how they make this MOSFET transistors, right? So from now, we always draw the MOSFET device like from the cross section. But in fact, you should always remember this device has some width. It's 3D, right? It's just from the side. So you just remember that this device has some widths. It's not just 2D. So here is just showing some of the values, typical values for the devices. For example, it's saying that this region from this side of the connection to the other side of the connection, the length is, for example, is like 90 nanometer. So you might have heard about the advanced CMOS or MOSFET or transistor nodes for the processors and things like 5 nanometer, right? Or less, or before was 22 nanometer. The older one was 19 nanometer, right? When you buy the processors, they usually say that this is like 5 nanometer device like that, right? Actually, they are talking about this length. They are talking about this length. The minimum feature size that they can build for the transistors in the more advanced technology now reaching like 5 nanometer. Several years ago, maybe 19 nanometer was still very small size, but now it's reaching to 5 nanometer. So it means that they can reduce the size of this transistor as that small feature size, right? So this 19 nanometer is talking about how small the channel is, because why we call it channel, because this is the point that the current has to pass from one side to the other side. This is the channel of the device, right? So let's see how it operates basically. So here is starting with this situation that let's assume that the both side of the channel, in fact, is grounded. And then we are trying to add some positive voltage to the gate. And we have this P substrate, right? So if nothing is there, let's say everything is just zero. In fact, you have like the PN junctions, right? Because the substrate is P-type material, you have this N-type materials or over here, right? So it's like a PN junction, right? So the PN junction initially has some built-in, like say, make some built-in depleted area, right? So this depleted area initially there is free of charge, free of uh, moving charge basically, right? So initially there is this channel basically is kind of open. There is no way that you can have free electrons or holes that pass through, right? Because of the depletion region is there already. And if you apply some gate voltage, positive gate voltage, because of this kind of capacitive region of here, so some positive charge will live on this part of the cap and some negative charge go up. And this negative charge now are free. In fact, their free electrons are forming under the channel region, basically. And once this happens, then the transistor can conduct, right? So basically, this is how this transistor works. When there is no DC voltage, this region of the channel is depleted. So there is no free electrons to pass. But once you apply a DC voltage, then because of this capacitance, it tries to absorb some of the free electron from the substrate and bring it just underneath of the channel. And then the channel will form because these electrons are free to move, right? The channel forms, right? So in that case, that sense, you can tell that if the channel is like a resistor, basically, right? From the left to right, If the gate voltage is not there, then this resistor is too big because it's like an insulator. And once you are increasing the gate voltage, you are basically bring some negative charge right here, and this negative charge can move, so it kind of reducing the resistance value because you still you can do some conduction, right? If you increase the voltage more at the gate, basically you are bringing more positive charge here and more negative charge here, right? So you have more negative free electrons here, right? So the resistance will be less, right? The resistance of the channel will be less. So oh, so again, it's here is trying to demonstrate what will happen once we are changing the VG. Now we are assuming also we are trying to pass some current from the one side to the other side, right? We have this VD, basically. The VD is not zero. We apply some voltage so that we allow some current to pass, right? So what is happening is that if the VG is zero, basically there is no channel, right? So there is no ID, the drain current, right? And then if we increase the VG at certain point, this channel is getting formed here, right? It formed here. And then if you increase the VG furthermore, then you will see that the current is flowing. The ID increases, right? Basically, the characteristic is pretty much similar to the transistor, BJT transistor. Over there, we had the VBE and IC, right? You need to reach at least around 0.7 volt, the VBE on, and then the transistor's getting turned on, right? Here is pretty much similar to that, but in here, actually, the V threshold is different value. It's not like fixed value like 0.7. So they can adjust this value to be different once they are building the transistors. And on the other hand, if you change the VD, basically you are saying that this channel is like a resistor at initially. So it has some sort of resistance that we can calculate it, right? It depends on how much VG we applied. If we apply more VG, the resistance will be less. If we apply less VG, the resistance is high, right? So some other things from the physics of this device you can basically tell is that so this oxide layer has some thickness of the oxide layer. So this oxide layer actually tells that how big the capacitance between the two metal is, right? So as a capacitor, you have two plates, basically, right? Some dielectric and some distance. If the distance is less, the capacitor value is what? Is bigger, right? If the distance is higher, the capacitance is less. And then if the capacitance is bigger, the stored charge is what is bigger with a certain voltage, right? So if you make your MOSFET with a thicker oxide or thicker isolator, the capacitor is smaller, right? So once you apply, let's say 1 volt to the gate, then the charge stored at the both sides is how much is less because the thickness is bigger, right? Comparing to another transistor, which the oxide is thinner. It tells that with a certain, I mean, with the same voltage for both of the case, one can store more charge. The thinner can store more charge, right? The more charge means more negative charge at the channel also, which means what? This negative charge supposed to conduct, right? So means that if you use a thinner oxide actually with the same value of the Vg, like let's say 1 volt, can conduct more better than the one with the thicker oxide, right? Because it absorbs more free electron. Because of the capacitance is higher, can absorb more charge, right? So the conduction should be higher. This is just saying the same thing, right? Saying that
If it was too big, then the capacitor is gonna be huge. So more charges are gonna be.
the capacitor in terms of the volume, you say it is big. No, let's assume like this. So basically you have two cases, right? Here is the semiconductor bottom. The top here is the isolator, and then here is the top plate, right? So the capacitor, this length is fixed, let's say. Now we have the other case. The isolator is thinner. The length is same. I'm just comparing, just changing the thickness, right? You need to, and then you apply some voltage on top, from top, right? Which,
Above one. Above the length. Be shortened.
oh yeah, that the length, so yeah, there are two things. So first of all, let's say just the length is fixed and we are changing only the thickness of the dielectric, right? Yeah, I just assume the thickness is, the length is fixed so far. The length is fixed. You are just changing this gap between the capacitor, basically, right? The area of the cap is similar. The area of the cap is similar. You are just changing the thickness. So if the smaller thickness actually increase the cap value, and once the cap increase with the same voltage, you have more charge, right? Yes, the other case basically is changing the length of the device, basically, right? You can make the device longer or shorter, the channel basically, right? The channel is shorter or longer. The shorter actually channel basically has less resistance, right? Because it's just a series. The electron has to pass through one side to the other side, right? The electron should pass all this distance, right? Under the channel length. So if the channel length is larger, or then it means that electron is seeing larger series resistance.
The capacitance is gonna be bigger.
The capacitor is bigger, but it doesn't. In fact, that's true. In fact, the charge density is important. In fact, the charge density is important. So, though they're increasing the L, you are increasing the capacitor. But this charge is just uniformly, you can say that it's distributed over the whole region, right? And then, in fact, though the number of charge overall is higher, but the density of the charge is not that different. So in fact, the electrons has to pass a longer pass that increase the resistance, right? Yeah, that's true. And the other parameter that in these devices you have is the width of the device, basically, right? We were talking about this L, we were talking about the thickness of this oxide, T oxide, right? And then the effect of the width. What if you increase the width? In fact, increasing the width is kind of making some devices parallel to each other, right? You could say that these devices are the wider device is like the parallel of the two smaller device, as you see here, right? The wider the device means you are somehow paralleling many smaller devices, right? So what you expect is that once you parallel the more devices, so the current should increase, right? Like you are paralleling several resistors, right? Once you parallel several resistors, the resistance value will be less, so the current should increase, right? Basically, the width is just a paralleling factor. So if you want to have the higher current, so you just parallel multiple resistors, right? To reduce the resistance to increase the current, right? So this several parameters you can tell from the physical structure, right? So I guess we can stop by here today. Right, so tomorrow we need to go a little bit more into the details of this. And then I guess after this part, we can very actually the architecture, we can pass it so fast. So this section, initially introduction of the device is more important. Yeah. You have any question? No question. Okay. So see you tomorrow, inshallah.